The fermentation and storage cellar, as well as the BBT area, but also e.g. the malt silos and the brewery, place high demands on a well-solved logistics. Unwanted mixing of materials must be prevented. A sensible management of the different attributes of tanks and silos, and especially of the pipelines, is managed in corresponding new classes. By using appropriate filters, the operator can make pre-selections from a multitude of objects in the existing tanks. In combination with root control or by classical control, the control of valves and motors is still organized. The use of these individual functionalities within the system enables an efficient and functioning cellar management. My colleague Horst Fuchs will now show you, using the SIMATIC S7-1500 controller as an example, what this actually looks like in the BRAUMAT system.
Thank
you, Jürgen. Now let's take a look at a classic automation solution in a brewery, where we are faced with the challenge of a fermentation and storage cellar. As we heard in the introduction, we'll use some of the new functions we established in the BRAUMAT system and combine them with, for example, root control. But we'll record a separate session for this. In this example, for the fermentation and storage cellar, we'll be using the bitfield function. We start with a tank class or object. This means that we have a new class here within the AS, for which there is also a faceplate. This class collects all the information that is relevant for a tank or silo. Of course, these are analog values, such as cooling zone temperatures, pressure, quantity. But there are also logistical attributes, such as tank status, in other words, I am full, I am empty, I am being cleaned, I am sterile. We have a quality status in which we say, I'm in a status where the operator may have acknowledged and checked whether the tank is okay. And of course, material information. We also have a total quantity value, which is the book value or values. This is the amount we are or are planning to draw into the tank. This can or will usually differ slightly from the measured value. We also count the number of batches here. There is a certain degree of intelligence within the tank module, which I'll demonstrate using this example here. If, for example, we have sterilized or cleaned the tank, which I do manually here, and the operator has acknowledged it, a sterilizer timer with a predefined time will start. After this time, the tank should have been used, in other words, filled. If this does not happen, you will receive corresponding messages. Please re-sterilize the tank after this time. The same applies when cleaning or if you have carried out testing in general. So that's the intelligence within the module. There is also batch information, transfer the analog values, and the usual About window where, configured accordingly, you can enter your user-specific data. We'll see how this works when automatic mode is running. As a counterpart to the line, we have a word line here and a beer line here. We can now also use a line object or class. This is more or less a subset of the tank. It has slightly fewer attributes, but of course it also has material information and tells us what is happening in the line at this moment, such as whether there is water inside, material inside, and so on. Because these are BRAUMAT objects, you can also find the BRAUMAT objects in the parameterization. In other words, we will see a tank in the list here, a line here. The advantage of this tank object is that in contrast to before, when tanks were also integrated in BRAUMAT, but with normal standard tools, analog values, timers and so on, now we can summarize everything relevant to this tank in one central class and even carry out configurations. This means that you enter all the linking here, for instance for full and empty sensors, just like the analog values and information on how many cooling zones there are, material information and so on. So we need this class accordingly and have the same for every pipeline. It looks similar, although there are significantly fewer attributes. Then in order to sensibly transfer materials to or from tanks into other tanks or out of the tank farm completely, we need a material check. After all, we want to prevent undesired material mixes. You can imagine that certain areas might be undergoing cleaning, so there might currently be cleaning material in a given pipeline. I don't want my transfer order to cause a primary product, in other words wort or beer, to be transferred through a line that hasn't been rinsed first. So this is why we need material management, which is established within the recipe system. Here we enter all of the materials, assigned with IDs. These can be raw materials and the end product, but also all intermediate products and additional components that you add, like hops, yeast, cleaning water and so on. Organize it into groups and then you can enter your rules, also via the material management here. So here we see the source material with its successors, possible permitted successors. However, there is also the rule you can enter the predecessors here. Let's look at an example. If I had dark wort in a pipeline and then use the same pipeline for light wort afterwards, I obviously don't want the color to be distorted. Therefore, after dark wort, I only allow cleaning material, water or a nothing material, in other words, air. In contrast to a light material, I now choose a Pilsner wort here, I would allow all other brewery products. After all, unlike in the reverse process, a dark wort as a successor will not become lighter. So those are the global rules. If, for instance, we take a look at the most critical materials, SIP material, then in my example I only allow water, brewing water or cleaning water. Whatever comes before, and this rule is then created automatically, is of no relevance in this case. My least critical material would be water. This is a rule that the BRAUMAT system will generate for me based on the other rules I entered earlier. In other words, before and after water, anything is generally allowed. The last function I need for the combination is a filter dialog. We could find this, for instance, in the order system if we enter a new order and make a selection from the complete tank overview. It was always inconvenient to have to search for which tank was empty, which could be taken. Here, if we set a corresponding filter, and now you will probably also understand the status at the top, we can now select which tanks are currently empty in this tank farm based on tank status. Incidentally, we are referring to the PCU3 here. In other words, tanks 1, 7 and 11 are showing empty based on their tank status. But if you want to refill a certain type of wort, you can also select a material and so on. We use this function if we are using control modules instead of root control. We can also use a further feature, the so-called bit field. This is a misused DFM, digital function module, which, thankfully, would also be possible as parameter transfer in the recipe system. Here are the individual values. This is not a 30-bit value, it's not an analog value, but rather I use my individual bits to control the corresponding control module. To demonstrate this, let's start a recipe so you can see what it's all about. So I have a word line as a subsystem. I have a beer line and of course a subsystem for each of the corresponding tanks. There are also prepared recipes. A filling recipe with a corresponding material compatibility test, destination compatibility test, and the actual controller, the corresponding valves. As I said, I transfer a DFM as mode mask in which I say, in this step, please fill the tank from the word line. This is converted accordingly in the AS in order to control the individual control elements. As I said, let's start a recipe, for example via the order system, in order to demonstrate which interfaces we can now find in our individual objects. Here is a recipe with the materials section. Let's make a deliberate mistake here. Let's say the job hasn't been done properly and it hasn't been rinsed and there is still dark word in the line. I have already simulated this and entered it in the corresponding object. In this next order, I'd like to transfer Pilsner word. The system should then respond accordingly. I select Pilsner word from the material list and select an appropriate amount. Here I have my filter dialog, which is already pre-assigned with Pilsner word, but I actually want an empty tank. So I use tank number 1 as a pre-selection. I start the recipe. You can then also see it online. I approve the recipe and let's see what happens. It activates the subsystem accordingly, and we are now requested via operator request to reconfirm that the Pilsner word material is the one we want. A material check is carried out, which duly fails because I have a material rule violation. Now it either wants a different, new material to be transferred, or I do it differently. I correct my mistake and tell it that yes, of course, this pipeline has been cleaned. I acknowledge the error, re-execute the operate request, and now we see that the material check works. Moves on, and now it wants me to confirm my destination tank once again. Here too, I can select this filter dialog again. Another test is done. Another material test within this object, but also within the status. If the tank wasn't empty, this wouldn't work. As you can see, even within the recipe jumps, the corresponding tank status information is now tracked in this tank object, and I get this material and status information tracking by setting corresponding bit masks here. We can also see in this bit field here that the checked control modules are activated And the response, and that's why it is green, also tells me that the selection was successful. The corresponding valve or motor is opened. So now we can see here that via this valve and motor combination, we are now transferring 50 hectoliters from the word line. Here is the book value. Here is the actual value. Here is the batch number. Meanwhile, perhaps you have also noticed that we also have a tank recipe that was started automatically in a loop. This means that as soon as the transfer starts, the Tank 1 subsystem also starts to run. The filling procedure has now taken place. We have transferred these 50 hectoliters, or in this case a little more. Now this tank is waiting on more commands. On the one hand, I can now switch to fermentation, but I could also wait for another filling order to arrive. After all, the tank is nowhere near full. It holds 500 hectoliters, so I start a tank order again. This time I don't use the order system. I can also integrate it into the process image. There are no more queries about the material. The material has already been pre-assigned. Pilsner wort. Here in the subsystem status field, we see the corresponding steps and my tank recipe continues accordingly. This is a loop. It has jumped back and is carrying out the second filling process. Here we see that water is always pushed out onto the drain first, in order to ensure that no old material remains in the line. The next transfer is then initiated. 100 hectoliters, or 2 times 50, second batch. In trend, we can also see it's a circular buffer, how the level increases accordingly. Okay, so we can take a look at the whole thing again in trend. Here is tank number 1, with the current batch. I'm going to hide a couple of things that we don't need. This red line is the filling level in the tank. This dark red is the book value, and up here we have pressure and temperature. I want to speed the whole thing up now. So let's imagine the tank is now full. I switch this operator request to start fermenting. Then, as you can see, the corresponding cooling zones are activated. The relevant valves are opened, the temperature decreases, and we find ourselves in the logistically independent step of fermenting. This means the filling and emptying, both units, do not play a role in these steps. So this is why we can now always run tank recipes independently. There is also no synchronization between the corresponding units. This tank now runs autonomously, perhaps for several days or weeks, and can continue its fermentation in peace. Of course, you'll notice that there is a lot missing from this example: yeast propagation, CO2 recovery, and so on. In this example, we are just looking at beer and wort transfer to make things simpler. You probably wouldn't find such a process image in the real system. Okay, the temperature drops. We also see the step curve here. The temperature goes down to a specific target value. At some point you would say fermentation complete. And then we move to store. Cooling happens here too. Perhaps you noticed there is of course a material change here, as the Pilsner wort changes to Pilsner beer, and after storage, the tank is ready to empty. empty means I can now combine it with a new subsystem again. I can control this again through the order system. But I can also make a selection in the process image and start an order accordingly. Or a batch, which is running now. This is synchronized again via handshake signals with the actual tank recipe that is underway. This means that the tank recipe is currently undergoing the empty step. We channel the corresponding new product through the beer line to filtration and empty the tank. Again, this can be seen in the trend image. So that was the tank phase, in which it reacts independently of the wort and beer lines and ferments and stores the beer. And now we are back at empty. Of course, parallel to this, we can use the wort line to fill another tank without any problem. There are many processes that run parallel in such a tank farm, and as long as I don't completely occupy a transfer route, I can execute corresponding transfers within this fermentation cellar. So we have seen how to combine various functions from BRAUMAT version 8 in order to execute such a complex cellar project. In another session, we will see, in connection with the root control function, how to activate the control elements in a different way. Thank you.
Siemens. Ingenuity for life.